Yeah, maybe let's get started. Yeah. So today we're quite happy. I mean, to invite Dr. Yuping Lin from UC Berkeley to give our talk. And Yuping is currently doing a postdoc with Joe Moore. I originally invited Joe Moore, but Joe Moore has a very a difficult travel schedule, so cannot make it. So he highly recommended Yuping. So I wanted to give junior people a chance to talk in this sort of forum and present themselves. Yeah. So he got his PhD degree from University of Colorado in 2022 last year, and has been doing fantastic. And now it's a sort of a named postdoc at the UC Berkeley. Yeah. Okay, Yuping, it's all yours.
Okay. So thanks to Clinton for the introduction, and thanks to everyone here for coming. And I'm Yuping from Berkeley. I'm currently a postdoc. So today I'm going to tell you about the story on the kagome Flatband. And this is about what our recent discovery of a phase diagram with some very interesting electronic phases. So the content of this talk will be, are mostly in our recent preprint here, and you could check it if you're interested in. Right. So before I go into the detail of my talk, I'd like to first present my acknowledgement to the Berkeley people. So this is a campus picture of the Berkeley, and our CMP group is around the 5th floor of this building behind the tower. Yeah, so I'm very, thankful to the people here. And this work is done under supervision of my advisor, Joe Moore, and also collaborated with my brilliant colleague postdoc Chen Xiao at Berkeley. Yeah. Okay, so here's an outline of my talk. I'll start with the background introduction of the recent excitement that people found in the frustrated kagome, Flatband materials, including kagome perichlor, etc. And then I will particularly focus on the kagome Flatband, where we study the repulsive electrons. And the first part of our work is done in the pure Hubbard model, where we only have on-site repulsion, and it will be across all the fittings of the Flatband. Then I will flash through our introduction of the extended repulsion and show some of the phases there. And to convince you that our work is not just theoretical, but we have some relevance to the real world, I will try to present some relevance that we think will be in the experiments. And then I will tell you what could happen beyond mean field theory, because our work is mostly done in the mean field level. And I will end up with a summary. So first, let me do a background introduction to our talk. So I believe everyone here are familiar with interacting electrons in the crystal studies, but let me do a brief introduction here. So we know that if we have the free electrons in the crystals, the dispersion energy of it will be periodic in momentum, and it will form a band structure, for example, like this. And the fermions will pile up from the bottom of the band because they have to obey the Fermi statistics. And the top of it will be the Fermi surface at the Fermi level energy. So now if we introduce an interaction U, then the interaction will open up a narrow interacting window around the Fermi level. And the window defines which electrons can be involved in the interactions. And now our question is, when we have the interactions, what would the free electrons become? So it turns out that, if we are at high enough temperature, the electrons are still effectively non-interacting. So and we call them Fermi liquid. But if we go to low enough temperature, it turns out that there will be some instability accompanied by the symmetry breaking. So how do we see this? So the symmetry breaking can be characterized by an order parameter, which we call delta. And by defining an order parameter, we can rewrite the free energy of the system in terms of it. So we can monitor the feature of the free energy as the temperature changes. For example, if we are at high enough temperature, the minimum of the free energy will be at the 0 order parameter, so that the Fermi liquid is not changed. But if we go to low enough temperature, it turns out that the minimum of the free energy will go to finite order parameter. And this kind of change will actually break the symmetry. As you can see, if we consider a symmetry transformation that change the state at positive delta to the state at negative delta, then we are looking at different ground states under this symmetry transformation. So we call that the symmetry is broken by the ground states. So these are the theoretical pictures. And in the real world, we have many different types of symmetry breaking orders. For example, the most classic one will be the ferromagnetism, where we can think of the order parameter as just the magnetization, and it breaks the spin rotation symmetry. And in addition to spin rotation symmetry, we can further break a translation symmetry in the space so that we will have a spin density wave which modulates in space. And we can also just break the translation symmetry, and it will lead us to a charge density wave with charge density modulations in space. And also, if we break the particle number conservation, we are having a superconductivity. So one important question is, we are having interacting phases if the electrons are interacting, but where can we find the very strong interacting electron phases? So to know this, we need to know how to estimate the strength of the interacting electron phase. So a very rough estimate will be given by the number of electronic states within the interacting window. And we know that the interacting window is characterized by two scalings. The first scaling is the vertical scaling in energy, which is defined by the interaction. And the second scaling will be the volume of the Fermi surface in the momentum space, and it will be defined inverse to the bandwidth. So if we want to enhance an interacting electron phase, there are two ways to achieve it. The first is straightforward, that is to make it larger so that we are expanding the interacting window and we can involve more electronic states. And the second way is opposite, that is we make the band narrower so that we're involving more and more electronic states given a fixed interacting window. So, and particularly if we look at the second case and force it to the limit where the bandwidth vanishes, then the band will be roughly flat and we will call it a flat band. So there has been a lot of interest in the flat band in the past decade. And one of the reasons is that because the whole band are not could not be covered in the interacting window, we can have very strongly enhanced interacting electron phases. And the second reason is that the flat bands are usually accompanied by very high tunability in terms of doping or band structure, etc. For example, we can use gating or like adding the magnetic field to change the feature of the of the system. So in experiments, there could be a large family of the phases that could be observable by the experiments. So now we know that the flat band is good. And the question is, where can we find the flat band in the materials or the, experimentally accessible systems? And there has been a lot of flat band systems that have been proposed, like Mare, for example. But today I'm going to focus on another family of the flat band materials, which is in the frustrated systems. Though it has been known that if we have the frustration on the lattices, for example, in the kagome particle or leaf lattices, then we can have the flat band in the band structure. For example, in the kagome lattice, we have the flat band at the top of the band structure. And for particle, we have doubly degenerate flat bands. And for a leaf lattice, we have a middle flat band. So what is the reason why these lattices have the flat band? So this could be understood easily from the destructive interference of hopping. So let us take kagome lattice as an example. If we put a wave function with opposite signs at the two sides here, and we look at the hopping onto the third side here, then we'll see that because the two sides have opposite signs in the wave function, their hopping to this side will cancel with each other, so that the third side will remain zero density after the hopping. And if we put the opposite sign wave function around a single hexagon, we'll see that even under the hopping of a Hamiltonian, the wave function will not spread and it will remain invariant under the hopping. So the eigenstate, so the wave function will be eigenstate of the Hamiltonian, and we call it the compact localized state. So these compact localized states are the elements of the flat band. So the kagome lattice, for example, will host a naturally natural flatband from the frustrated hopping. And similarly, we can do the same thing for particle and the leaf lattices and show that the flatband can come from the compact localized state. So now we see that the frustrated materials are a promising family to realize the flatbands. And an important question is, given these frustrated materials, which ones will host the flatband close to the Fermi level? Because at the end, if we want to see it in the experiments, we need it to be close to the Fermi level. And second, if we have the materials that, satisfy this condition, what are the interacting phases that we can see in the experiments? So these are two very important questions. So, this question has been addressed recently in the kagome flatband, compounds. And the first family is the binary materials TX, where T could be the iron or manganese or cobalt, and the X could be the germanium or tin. So the first identification of flatband in this family is in the iron tin material. And so what are the features in the iron tin materials? So the iron tin materials are quasi 2D layer materials. And if you look at the structure, you'll see that the iron atoms will form a kagome network, in each layer. And if we look at the high enough temperature in the non-magnetic phase, the kagome layers will have the flatbands, which is very close to the Fermi level, which is good. And if we go below a certain temperature, for example, around 400 Kelvin, it turns out that the kagome network will form the intra-layer ferromagnetism, so that there is a stoner splitting between the majority and minority spin bands. So this is what is found in the iron tin material. And more recently, it was discovered by the Rice experimental group, like Pengchen's group, that in the iron germanium, in addition to the intra-layer ferromagnetism, there is an additional 2x2 charge density wave, which occur at below 100 Kelvin. And the reason for this CW transition is that when we have the stoner splitting between the spin majority and minority bands, the spin minority band will have the Fermi level roughly at the Van Hoff singularity, so that the electron interaction can drive the charge density wave. So, we can see that, or in the flat bands, we can have very interesting interacting phases. So in addition to the binary materials, the ternary 135 compound has been extremely popular in the past few years. And these compounds usually have the AB3C5 structure. And one of the most classic example is the AB3VSB5. So, in this material, the vanadium atoms will form a kagome network. And in the band structure, we can see that the vanadium kagome network will contribute to the kagome band. And for the vanadium-based materials, the Fermi level is at the Van Hoff singularity of the kagome band. However, it has been shown that, this 135 materials has a very high tunability by substituting the elements. For example, if we look at the periodic table, we can see that the vanadium atoms are here. And if we substitute it by, for example, a titanium or a chromium or magnesium, then we can possibly change the Fermi level to the other fittings of the kagome band. And indeed, it has been realized recently in the other materials. For example, in the titanium-based materials, we can see that because we are going one electron lower in the periodic table, the Fermi level is tuned below, and it is actually approaching a lower flat band in the band structure. And more recently, actually within a month from now, in the past month, there is a chromium-based material where, because chromium is one electron higher than vanadium, the Fermi level is tuned upper, and it is actually approaching the upper flat band of the band structure. So, if we can tune the elements of the ternary compounds, maybe at some moment we can find the materials where the Fermi level is really at the flat band, in the flat band, so that we can see what interacting phases they have. And in addition to the kagome metals, more recently, it has been shown by the right experimental group again, for example, Punchen and Mingyi, that the Syrian dirutinide actually also holds the flatband close to the Fermi level. And one interesting thing about this compound is that in addition to the ferromagnetism below 40 Kelvin, there is also the superconductivity below the 6 Kelvin. So this is one of the, promising example where we can find flatband superconductivity. Yes. Are there questions or?
No, I mean you can keep going. Most people typically ask at the end. Yeah.
Okay. Thank you. So so these are the experiments that we have seen in the frustrated flatband materials. So up to now, the current experiments that we have seen are only observing the ferromagnetism from the flatband. However, we know that because the materials we're considering are having frustrated lattices, and there has been many theoretical works proposing many possibilities of magnetism or spin liquid or topological phases. For example, for a kagome lattice, in addition to the ferromagnetism, there are also 120-degree coplanar orders and octahedral orders for the more exotic cuboid orders. And beyond the mean field level, there is also the proposal of the chiral spin liquid and also the non-chiral spin liquid. So our question here would be, can we see more interacting phases than just the ferromagnetism if we look at the kagome flatband materials? Okay, so so this summarizes the background introduction to my talk. And now I want to put my focus on a particular class of this family, that is the kagome flatband. And I will tell you what would happen if we have repulsive electrons on the flatband. Okay, so here let me do a very brief introduction to the kagome lattice. We know that the kagome lattice has a lot of ingredients. For example, there is a triangular Bravais lattice site, and at each Bravais lattice site, there are 3 sublattices, which can, for example, form a triangle. And because we're considering the spinfold fermions, we will have a double degeneracy in the spins. So the model, the non-interacting model we're considering is a tight binding model, and we will consider just nearest neighbor hopping, like this. Yeah. And because we're having a triangular Bravais lattice, our Brillouin zone will be hexagonal. And because we have 3 sublattices here, in the Brillouin zone, we will have 3 bands. And here we'll be focusing on the flatband. And as such, I'd like to define a new flatband fitting NFB, which is with respect to the half-field flatband. So when I say that NFB is equal to 1, I'm referring to the empty flatband, and there is actually a quadratic band touching here. And if I say we're looking at NFB equals 0, I'm telling about the half-field flatband. And similarly, for NFB equals 1, I'm referring to the fully filled flatband. Okay.
Please mute your microphone.
Yeah, sorry. I've been hearing different sounds. I'm a bit confused. Okay. So as I mentioned previously, I want to consider the repulsive electrons on the lattice. And so here I will be introducing a density-density interaction to the model. And here, at first I will focus on the on-site repulsion, where I define a U not greater than 0. And with only nearest neighbor hopping and on-site repulsion, we can say that it is a pure Hubbard model. Okay, so we know that the interacting electrons are generally hard to understand and hard to solve the problem. And there are many different types of first steps that we can do to decode this problem. And here the first step I'm going to take will be to map the problem onto a mean field theory, where we're looking at an effective single particle Hamiltonian, and this is called the Hartree-Fock analysis. So how do we do this? Well, if we can first look at the interacting model and focus on a particular green electron, So the green electron will interact with many of the surrounding electrons, which we call the blue electrons. And this process will involve the C dagger, CC for fermion interaction. So we know this problem is hard to solve, so we do a mapping. And the mapping is called the Hartree-Fock mapping. So the first step is that we can, if we choose the green electron, we can group all of the remaining, blue electrons into an background environment for the green electron, so that the interaction between the green electron and the blue electrons will become a background potential for the green electrons. So the interacting problem becomes an effective single particle problem. And there is an additional feature that we need to know about the fermion. That is, because the fermions are identical particles, the green fermion can also merge into the environment and become a partner of it. And as a replacement, the environment will eject a fermion outside, and it will become the new green fermion for our theory. And this is called the Fock potential. And this is also a single particle process. And because it involves the Fermi statistics, there will be a minus sign here. So in the Hartree-Fock mapping, we will have an effective single particle Hamiltonian for us to solve. So we can just diagonalize it and try to minimize the energy self-consistently. And by doing this, we can get the ground state, and we can analyze the symmetry breaking orders of the ground state to see what basis we're looking at. So this is a very brief introduction to the Hartree-Fock analysis. Now, you may think that the kagome lattice is has a long history, and Hartree-Fock analysis will be straightforward to apply to it. So people might have done this before, and indeed there has been a lot of literature on this. So it has been shown back in 1995 that they did a very simple Hartree-Fock analysis to search for the ferromagnetism on the kagome lattice. And if we look at the flatband regime, which is the red rectangle here, we see that in the flatband regime, there is a large occupation of the ferromagnetism in the phase diagram. However, this analysis, because they focus on the ferromagnetism, for the non-ferromagnetic orders, they only take one additional ansatz to put into the phase diagram. So they cannot really find the true ground state, and the analysis is incomplete. Secondly, people have paid particular attention to the half-field flatband. For example, back in 1992, Mielke applied the combination of graph theory and percolation theory to claim that the ferromagnetism is a mathematically rigorous ground state under the on-site repulsion. And more recently, in 2021, Donald Shen's group has done a DMRG on a TJ model, and he found that if we add an extended repulsion, there could be a quantum anomalous for ferromagnetism and also some ferromagnetic charge spread. However, we know that the TJ model only applies when we have the on-site repulsion much larger than the extended repulsion. So we may be able to extend this phase diagram beyond this regime. Thirdly, people have paid a lot of attention on the empty flatband, that is NFB equals -1, back around 2010. And for example, some of the Hartree-Fock analysis have mapped out a phase diagram with a lot of spin and or charge orders. However, in their Hartree-Fock analysis, they have assumed the translation symmetry between the unit cells and the spin collinearity for the spins in their phase diagram. So they cannot see the states like 120-degree antiferromagnetic order or the tetrahedral order. So the phase diagram is also not complete in this sense. So after we found that the previous analysis may be incomplete, we try to do our own Hartree-Fock analysis. So let me now show you briefly the result. So first, we look at the phase diagram across the flatband. And in addition to the ferromagnetism, we find a lot of many different phases from here. For example, we have the stripe orders and also the non-colinear orders like 120-degree spin order and the noncoplanar order. Secondly, we also add the extended repulsion to the model so that we can see some additional orders from the original phase diagram here. And thirdly, we have revisited the empty flatband, and we see that the non-colinear order, like 120-degree antiferromagnetism, is actually very important. And you can see a very brief comparison with the previous analysis. For example, for the cross-flatband phase diagram, we see a lot of new phases here, which occupy roughly this regime. And for a half-field flatband, we're extending the original phase regime to see a lot of new phases here. And for the empty flatband, we are seeing the importance of the 120-degree order in this regime. So one question might be, what have we done differently from the previous studies? So first, our Hartree-Fock analysis involved a spatially unrestricted formalism. That is, we do not put any ansatz or constraint on the wave function. And in this case, if we are minimizing the energy, we're able to really go to the true ground state, at least at the mean field level, without any bias by the ansatz or the constraint, like translation symmetry, for example. Secondly, we do a very serious complete scan of the phase diagram so that we can see many, interesting phases that has never been found in the previous literature. That is, we're finding new magnetic orders as the major members of the phase diagram. And in the following, I will be going into some details of our work. And because I do not want to lose the attention of you, I want to first briefly summarize some highlights of our work. So first, but from our Hartree-Fock analysis, we are able to find a lot of, stripe and non-colinear, spin orders, and they will form the cascades when we are looking at various fields. And most of the orders we find haven't been found in the previous literature, so we're finding new magnetic orders. And second, we try to, because we're doing the theoretical work and we want to make it more relevant to the real world, so we try to fit the practical materials like iron tin and iron germanium in our phase diagram. And we are able to locate them roughly in our phase diagram. And by doing so, we are able to predict, for example, where can we find noncoplanar or stripe orders when we are trying to search for the related materials. Okay, so after the brief summary of our highlights, let me now go into the details of our work. So first, I will tell you about the pure Hubbard model across the kagome flatband. So as we have seen previously, there is a very strong ferromagnetism across the flatband. So if we, for example, look at the regime above the flatband, half-field flatband, it has been proposed in 1992 by Milky that there is a ferromagnetism to paramagnetism transition from the percolation. And indeed, we also see it in the Hartree-Fock analysis. So now our question would be, what will happen if we go below the half-field flatband? And and you can see that the ferromagnetism has a pattern like this. In a charge pattern, we do not see anything. And in the spin pattern, we will see a uniform ferromagnetic order here. Okay, so first, if we look at the large ulnar region below the half filling, we are looking at the ferromagnetism across all of the fillings here. So as we know, ferromagnetism is very important on the flatband. So we can look at the band structure of the ferromagnetism under the Stoner splitting. For example, if we look at the empty flatband, we are looking at actually the overall 4/6 splitting. And if we have the Stoner splitting between the spin majority and the spin minority bands, we will fill 4 out of the 6 bands under the Stoner splitting. So the Fermi level will be at a direct point. Meanwhile, if we look at the half-field flatband, that is the overall 5/6 filling, we will fill 1 additional band in the spin minority bands. So we will have the Fermi level at the quadratic band touching here. So these are the 2 major fillings of our system. And we know that the splitting energy under a Stoner splitting can be estimated by the on-site repulsion and the density imbalance between the majority spin and the minority spin fillings. So now our question is, what splitting energy should we have for the ferromagnetism to be stable? And we know that if we want to stabilize the ferromagnetism, we may want to saturate the ferromagnetism such that we're pushing the spin majority bands low enough and we're fully occupying the majority spin. The reason is that if we have the Fermi level of the majority spin, above the Fermi level of the minority spin, some of the flatband electron filling might just percolate into the dispersion bands of the minority spin bands, so that we're destabilizing the ferromagnetism. So we want to saturate the ferromagnetism to make it stabilize. So first, if we look at the half field flatband, we can see that as long as we have a finite splitting, we are lowering the spin majority bands below the Fermi level of the minority spin bands. So the saturation repulsion will be at infinitesimally small. And as you can see in the phase diagram, indeed, as long as we turn on the repulsion, we're having already the ferromagnetism, which is good. However, if we go to the empty flatband, that is at this splitting, then we will see that we need to have a finite splitting to saturate the ferromagnetism, that is to push the majority spin bands below the minority spin Fermi level. And here our estimation will be around 4.5. So by doing this kind of estimation, we can see that the ferromagnetism is actually destabilized as we are pushing the filling below the half field flatband. So if we go below the half filling of the flatband, the destabilized ferromagnetism will allow the room for the other magnetic order to occur. So our question is, what will happen when this happens at the moderate U-0 regime? So the first series of the other magnetic order will be the spin and charge stripes. So for example, if we first look at the empty flatband, that is the regime here, and if we look at the charge pattern of the ground state, we'll see that although there are some higher and lower density charge density stripes, the translation symmetry between different unit cells is not broken, so we have a periodicity 1 for a charge stripe. However, if we look at the spin sector, we will see that the higher density stripes are actually having antiferromagnetic stripes between different unit cells. So the magnetic order is actually breaking the translation symmetry and enlarging into 2. Now, if we go from the empty filling to the half filling of the flatband, we know from previous slides that we're looking at the ferromagnetism. And we know that the ferromagnetism is uniform in the whole space. And we can think of it as a periodicity infinite, the spin and charge stripe. So now we have seen that we have periodicity 1 at the -1 filling, and we have infinite periodicity at the 0 filling. And we may expect a gradual increase of the periodicity as we increase the filling from -1 to 0. So indeed, if we look at a state in between, we are seeing the cascade of the spin and charge stripe order with increasing periodicity. For example, if we look at the negative half filling of the flatband, which is half filling between -1 and 0, we're seeing that the charge periodicity is becoming twice, and correspondingly, the antiferromagnetic stripe is also increasing in periodicity. And if we look at the -1/3 filling of the flatband, we can see that the charge stripe periodicity is tripled, and also the AFM periodicity. So we are seeing a very elegant spin and charge stripe cascade of PM periodicity for a -1 of 1/n filling. And the very good intuition for this is that as we are increasing the filling from -1 to 0, we're gradually filling the lower density stripes. For example, if we go to the -1/2 filling of the flatband, so that we're filling we're looking at the half filling between -1 and 0, we're filling half of the lower density stripes. So we're doubling the periodicity. And if we look at the negative 1/3 fitting, we're at the 2/3 fitting between -1 and 0, so that we're fitting 2 out of the 3 lower density stripes. So this is a very intuitive way of understanding why we have the cascade of the spin and charge stripes.
So experimentally, none of the state is seen, right? None of this is
yeah. That's a very good point. So as I will say later, right now we think that the current materials are all at a very strongly repulsive regime, so that we do not see the lower repulsion interacting phases here. So that is actually one of the proposals that we want to make, that if we can find the materials with weaker correlation, maybe we can see these kind of orders.
Okay.
Yeah. Yeah, so I will focus on this point later. So we have seen the spin and charge stripe in this region. And next I want to move a little bit higher in the repulsion and look at some non-colinear orders. For example, if we look at the -1 fitting here, that is the empty flatband, we find that we can see a 120-degree triangle ferromagnetism. Antiferromagnetism. That is, if we look at a spin sector, we can see that within a unit cell, we are seeing uniform spin orders. But if we look at 3 nearest neighbor triangles, we will see that the magnetic orders of them will form a coplanar 120-degree order. Now, if we add a doping of it, that is, we increase the doping from empty fitting to finite fitting. And for example, if we look at -5/6 fitting, which is 1/3 fitting between -1 and 1/2, we're looking at the tetrahedral canted triangle spin order. So as we increase the fitting, we would expect the periodicity to be enlarged. And indeed, within 3 triangle unit cell like this, the charge will accumulate at one of the 3 triangles. And if we look at the 3 spins on this higher density triangle, we will see that they form a canted structure like this. Now, if we look at the nearest neighbor for higher density triangle, for example, this one, and this one, and this one, and this one, we will see that the magnetic orders will form a tetrahedral structure. And they will be accompanied by the lower density magnetic orders, which will be the corner of this polyhedron. So we're seeing an extensive non-coplanar orders as we increase the fitting from the coplanar 120-degree order. And if we now go a little bit higher into -2/3 fitting, that is, 2/3 fitting between -1 and 1/2, we will see that because the charge density is increased, the higher density will now be the center hexagon of 3 nearest neighbor triangles. And if we look at the magnetic order within this hexagon, we will see that the 6th magnetic order will form the 6th red coplanar order. And because they are winding around the plane, we call it the hexagon spin vortex. And now if we compare the magnetic order on 4 nearest neighbor hexagons, we will find that the normal vector of their planes will be tetrahedral to each other. So we call it the tetrahedral hexagon spin vortex order. And this order is actually related to the previous mentioned Hubbard order, because if we look at the lower density magnetic orders, the lower density lattices are actually forming a kagome structure, and the magnetic order will be corner of the polyhedron, and that will actually be the Hubbard order in the previous discussion. So one key message is that as we increase the fitting from the coplanar 120-degree order, the fitting not only increase the periodicity, but it also breaks the coplanarity and bring the magnetic order into the non-coplanar spin orders. So here is a brief summary of our discovery in a pure Hubbard model. So if we look at the large unit regime, we're seeing the ferromagnetism. And if we look at moderate unit regime, we're finding many new states. First, we will have the cascades of the spin and charge stripe. And second, we will find the evolution from the 120-degree coplanar order to the non-coplanar spin orders. And I want to briefly mention that if we look at the boundary of the ferromagnetism, we will actually find the spiral spin orders. And if we look at the very small UNA regime, we will find the ground state to have the dilute compact localized state. So this is a very brief summary of what we found in the pure Hubbard model across the Flatband. So, currently I have been focusing on the case where we only have on-site repulsion. And I want to briefly tell you what I found. What we found when we have the extended repulsion. So, for example, if we look at the half fitting, and if we put the extended repulsion U1 equals size U2, we will find that there could be a quantum anomalous ferromagnetism. That is, in addition to the ferromagnetism, we can also have the loop current order, which breaks the time reversal symmetry. So the ground state could be a quantum anomalous insulator. And if we further increase the extended repulsion, we can see some, charge stripe. And if we increase it further, we can see the 90-degree antiferromagnetism, 120-degree AFM, and also some other different interesting orders. And if we look at now the empty field flatband, so this is the empty fitting, which is NFB equals -1. We will see that there is a very important occupation of the 120-degree coplanar order. And in addition to that, we can also see the charge density wave, which is here, and also some, the other type of the antiferromagnetic stripe order. And also we can see a very narrow regime of the quantum anomalous insulator where you have loop current, or the quantum spin hole insulator where you have the spin current. Okay, so this is what we found when we add the extended repulsion. So up to now, I've been telling you about our theoretical discovery, but I now want to convince you that our work may also be relevant in the experiments. So let me do a flash reminder of what has been found in the kagome binary materials. So in the iron tin, we have intralayer ferromagnetism, and in the iron germanium, there is an additional 2x2 CW from the Van Hoff singularity of the spin minority band. So our important question is, are these materials in our phase diagram? So first, although the practical materials are two orbital models, here we will use a single orbital model to do our fit. So first, we will estimate the fitting of the flatband from the fitting of the minority spin fitting, and we will get a flatband fitting from the fitting of this. And secondly, with the minority spin fitting, we can also estimate the on-site repulsion from the Stoner splitting, which is the splitting energy divided by the charge imbalance between majority and minority spin fittings. And by doing so, we can locate the iron tin and iron germanium in our phase diagram. The iron tin will locate at a higher density, and it is just in the ferromagnetic regime, which is consistent with experiments. Meanwhile, the iron germanium will be located here, and although we are having it in the spiral spin order regime, the three-dimensional and the multi-orbital nature may stabilize the ferromagnetism instead. And there is something more we want to say about the iron germanium. That is, we try to fit the nearest neighbor repulsion U1 from the CW splitting in the experiment. And by applying this U1 in the ferromagnetic ground state at this point, it turns out that we can find a 2x2 trihexagonal bond order in the ground state. That is, in addition to the ferromagnetism, we can also find a charge bond order where the strong bond will form a hexagon and a triangle. And this 2x2 trihexagonal bond order has been known as the CEW for the 2x2 order in the kagome Van Hoff singularity. So we are actually really proposing the relevance of our phase diagram in the practical materials. So as Pengcheng has asked previously, right now we think that the current materials like iron tin and iron germanium are all in a strongly repulsive ferromagnetic regime. And we want to propose that if we can find some materials where the Coulomb repulsion is reduced, then maybe we can get access to the noncoplanar orders or also the stripe orders. So this is our proposal. And actually, there are some recent experiments on the antimony substituted iron germanium, which is actually within a month past. So in their phase diagram, they found that if you substitute the antimony into the germanium, then one can tune the intra-layer ferromagnetism with charge density wave into some non-colinear order. So in their case, they proposed that it might be a 120-degree order, and they were doing a neutron scattering on the powder examples to see this. And maybe if one could have a single crystal, then people would be more, understand more what are really the non-colinear orders. So at the end, I want to briefly mention what could happen if we go beyond the mean field theory. So one possibility here is the quantum spin liquid. So in the quantum spin liquid theory, people have been fractionalizing the fermion into the fermionic chargeon and also the bosonic spinon. And the bosonic spinon will be the thing that we'll be focusing on. So we know that in the spin liquid theory, if we have a magnetic order at a momentum 2kc, we can think of it as a symmetry breaking instability of the spinons, and the corresponding condensation will be at a momentum kc. So we have seen a lot of magnetic orders in the Hartree-Fock, and our question here is, what could be the symmetric parent spin liquid from these magnetic orders? And very interestingly, my brilliant colleague Chen Xiao found one particular Z2 spin liquid, which could be the parent spin liquid order for our magnetic orders in the Hartree-Fock results. So Chen Xiao did a projective symmetry group analysis, and he found that if we focus on the ferromagnetism and the 120-degree order and the spiral order here at the empty feeding of the flatband, there is a particular Z2 spin liquid that can have the spinon condensation at this momentum and with the exactly consistent magnetic order to what we find in Hartree-Fock. For example, he can find the 120-degree order of this form from the spinon condensation in his analysis. So what does this tell us? And there's another thing we want to mention is that among these instabilities, the spiral spin order is usually a weaker instability of the spinons. So if we go beyond the mean field level, and for example, if we do DMRG or Monte Carlo, maybe the Z2 spin liquid can be the true ground state in the regime of the spiral spin order. So in summary, we may be able to see the Z2 spin liquid in this regime of the phase diagram if we do some beyond mean field analysis. So there are also some other possibilities for the beyond mean field result. For example, it has been long proposed that if we look at the fractional fitting of a topological flatband, and if we introduce the interaction, maybe we can see the fractional training status. And also, quite recently, Qimiao at Rice has done a theoretical work, and he proposed that there could be some quantum criticality from the Kondo physics if we look at a kagome flatband. And also, people have been studying the superconductivity by doping the magnetism, for example, on the triangular lattice. And for example, by doping the chiral spin liquid on a triangular lattice, people may see the D-wave chiral superconductor. So there could also be a possibility of non-trivial superconductivity in the kagome flatband. And right now we're exploring these possibilities with some beyond mean field techniques. For example, we are having ongoing DMRG work to see these possibilities. So this will hopefully I can present it to you in the future. And this brings me to a summary of my talk. So we have done a mean field Hartree-Fock analysis in the kagome flatband, and we have found many interesting electronic phases. First, we have seen the cascades of stripe and non-colinear spin orders in the feeding phase diagram, in addition to the ferromagnetism. And all of the things here, other than the ferromagnetism, are new in that is, they have never been seen in the previous literature. Secondly, I have proposed that we can, roughly locate the iron tin and iron germanium in our phase diagram. And by doing so, we propose that maybe if we could reduce the Coulomb repulsion in the materials, we could see the, very interesting orders like non-coplanar orders or the stripe order here. So, so we hope that we can see more interesting things in the kagome flatband. So this is the end of my talk, and thank you for your attention.
Okay, yes, thank you very much. Yes, quite interesting. Yeah, I'll have some questions, but we'll get Chanton to ask first.
Yes, sir.
You muted, Chanton.
Hi, Yuping. Very nice talk. Thank you for the talk.
Thank you.
So I had a question regarding whether or not. So first of all, can you comment on the ordering wave vectors of the different phases you've obtained?
Yes. So let me go to the slide of the corresponding. So for example, for the stripe orders here, this one will just be a 1×2 periodicity order. So if you look at the momentum of B, it will just be half of the endpoint on the in the hexagonal Brillouin zone. And if you further increase the periodicity, it will just be half of the endpoint, and 1/4 of the endpoint, or 1/6 of the endpoint. Yeah.
I see. So it's a function of filling. If you change your filling, you get different.
Yeah. So the wave vector will be corresponding to the periodicity in the real space order.
Okay.
So now, in this case, you have sorry, Chanton.
Yeah, please go ahead. Please go ahead.
No, I was just curious from experimental perspective. Do you actually mean the moment will be empty in one of the kagome irons? It's really like a local type of picture, right?
Yes.
So sort of like a John Tronquata stripe type of picture, right?
Yes.
Okay. But most materials you're dealing with is the metal, right? That's hard for me to believe this actually happens. Yeah, but
so that's a very good point. So if we, at least from our theoretical analysis, if you only have on-site repulsion, then the lower density site will be completely non-magnetic. But you introduce the extended repulsion, then generally this site could be magnetic also, but it will be have a much weaker magnetic order than the higher density sites.
Okay.
Yeah, and I expect this to be experimental relevance. Yeah, sorry.
Yeah, so I just want to complete my thought actually. So I think the question I have is whether or not the 2×2 order you mentioned, is it for a very fixed filling that you see, or is it over a range of fillings?
You mean these ones, or?
You talked about a 2×2 order that mixes charge and spin.
Oh, yeah. So let me go to this one. This one, right?
Yeah. Yeah. So this 2×2, what filling do you get it for?
So this is at the -3/4 filling, which is the Van Hoff filling of the spin minority band.
I see.
Yeah.
Yeah. So I just want to point out that we studied this in the case of both the vanadium and the iron germanium, and we also find this similar this kind of order which mixes the charge and the spin, and you get, depending on the filling, you can get striped orders, which is similar to what they found in experiment with with Emperor. But the key point is that in our work, it is important in order to obtain this mixing of spin and charge, you need to consider the non-trivial topology of the bands, and that seems to be key.
That's a very important point.
I'm wondering whether or not in your work you take into consideration any topological aspects of the band, or you just treat the whole thing as without spin coupling.
Yeah, so in our case, what we start with is a single orbital kagome lattice. That is the I mean, you have kagome lattice and you have tight binding popping on the kagome lattice. So we did not put, for example, the Z2 topological feature as in your work, and we just get a kagome, simplest kagome, right? Yeah.
Okay, all right. But do you think this phase diagram will change if the topology is taken into consideration, or do you expect it to be the same?
I think there will be some similarity, but I'm not sure about that. Yeah. I think qualitatively, I don't expect much difference, but the topology of the each of the ground state might be different.
Okay. So
Yeah,
Fang, you have a question? Fang Xie? Can you unmute yourself?
Hi.
Yeah, okay.
Hi, can you hear me? Yeah.
Yeah.
Hi, Yuping. Very nice talk. I want to ask some detail about these stripe-like orders labeled by P1, P2, P3. So it seems that they are living in the background of this AFM as the charge ordered phase, right? So when you slightly dope the system from, for example, minus 1/3 to some other irrational values, how much different energy change would you observe in that process, and how this difference would change with the filling factor? Say you have 1/2, 1/3, 1/4. Is it getting smaller and smaller?
So that's a very good point. So I mean, actually, if you're interested, you can check the appendix of our paper, and there we show that if you go away from these commensurate fillings, I mean, you could still have this kind of periodic stripe orders, but they may not be as elegant as what I have shown here. For example, you may have one stripe of spin down and 3 stripe of spin up, which is forming a ferromagnetic order, something like that. And the cases I showed here are all antiferromagnetic because they are, I mean, at the simple -1/n filling. Yeah.
So I guess it will be somehow like attracted to the nearest P/Q with co-prime P and Q, something like that.
Yeah, and, that's my impression.
I see. So I guess when Q gets smaller, you would have a more stable state?
I think so. Yeah.
Okay.
A ground state with larger periodicity seems to usually be less stable.
I see. Thank you.
Yeah, Ning, you have a question?
Yes, you've been very nice talk. Can I just ask on this phase diagram, suppose just for the experimentalist, suppose you're at the iron germanium point and you go down on the axis, what is the expected change in the band structure SU2 U naught over T1?
U naught over T1.
Like if you go down horizontally, I can understand you're changing filling, but like effectively when you walk
so that's a very good point. So if we are lowering the lowering the U naught, we're actually reducing the distance between the majority and minority spin filling. So you can see that, you can think that the majority spin bands are getting upper and the minority spin bands are getting lower. And at some point that they are close enough, there could be a hybridization between the empty bands here and the filled bands here, so that the ferromagnetism may be destabilized and some other magnetic orders may form. So that's our impression of some other orders can form when you have lower Coulomb repulsion.
So like if I were to measure the paramagnetic state for all of this, like along the vertical axis, that would look the same? Like, is there a way to? I don't know if I'm asking the correct question.
Are you thinking about the band structure? Imposing the ferromagnetism, but you still lower the.
Yeah.
I see. So that's a very good point, and that is why we think ferromagnetism will be unstable if you lower it. So, for example, if you raise the majority spin bands above upper and finally above the Fermi level of the minority spin band, then the occupation on the flatband here can start to proliferate into the minority spin bands. So you're gradually destabilizing the polarization of the ferromagnetism.
Okay.
As as you lower the repulsion and getting the bands upper and upper. Yeah.
I see. Sorry, just last question. So the distinction between iron germanium, iron tin, and the reason, I guess, of why you only see the CW in the iron germanium, at least in your picture, is that the filling is such that you're at the Van Hope for the iron germanium, but not for iron tin. Is that the
I mean, at least from our theoretical framework.
Okay, thank you.
Thank you.
Yeah, so I have a separate question. So in the case of iron germanium, it's also known that when you cool down to lower temperatures, the system actually become sort of incommensurate with some sort of spiral. Yes. Yeah. So how do you understand that based on your phase diagram?
So that's a very good point. So in my analysis, I have been focusing on the pure 2D system, but I think that in conventional order, I think also mentioned in your papers that it should be a 3-dimensional effect. That is, it should be happening between different. Yeah.
I see. Yeah, I mean, it's actually interesting. The recent experiment suggests that the anomalous Hall effect, I mean, is dramatically associated with the non-spin, maybe non-collinear order in such a system. So it'd be very interesting to see that if you guys can predict that after you transmit into a spin flop phase, what kind of a magnetic structure you would expect. I mean, that one can actually check.
Yeah, I see.
So to basically see whether the anomalous Hall is actually indeed anomalous Hall or actually topological Hall effect.
You're thinking about like if we add the third direction, that is
add the third direction, also turn on the magnetic field. You once you put into a spin flop phase, then I'm pretty sure that the system will become some sort of non-collinear spin arrangement. I mean, it turns out the non-collinear spin arrangement is not unique to iron germanium. It turns out that the ytterbium iron germanium is 166 is also sort of similar, and then, the system has ytterbium which has some sort of moment that can interact with iron. But in pure iron germanium, it's not clear, why you should have such a phase. Yeah.
I see. But is that 166 material also in the flatband fitting? Because I remember that might be closer to.
I don't think anybody has done that. I don't think anyone. I don't think it's clear in the case, but we haven't even published our first paper on that.
I see. I see.
Okay. Yeah. Thank you very much.
But thank you for letting me know about it.
Yeah. Thank you. Any other question? Yeah. If not, let's thank Yuping for giving such a nice talk. Yeah.
Thank you so much.
Yeah. Thank you.